we'll get started, okay? And thank you all for completing your homework and turning it in. Um, any feedback before we get started regarding the homework or what we covered last week? Confusion? Any questions? We're okay? So far so good? Yes, question?
Could you explain confounding variables?
Confounding variables? Sure. Let me get to that and then
Just when it comes to categorical variables, frequency tables only for categorical, or can we use that also for numerical?
frequency tables are generally for categorical variables, but they can also be used for a numeric variable because we are, I guess we can artificially implement categories in a numeric variable. So I guess the answer is both. Okay. Confounding variables. That comes up whenever we are looking for a cause and effect relationship. Okay. So a lot of times we do an experiment or some kind of study, and it seems that two things seem to be happening together. Okay. Maybe we see people who drink a lot of orange juice. Maybe they seem not to get as sick as often or something. Okay. We see two things happening together. Now we don't know. We don't know if one thing causes the other, okay? Does that mean orange juice is beneficial to your health?
No.
Or is there something else going on, okay? A confounding variable is something else that could be confused or mixed up with the variable that actually has the effect, okay? That's where confounding. So the word there is kind of the root of confusion, confounding. It's the idea that maybe one thing you cannot distinguish one from the other. So, for example, let's say I did an experiment and I had some subjects drink whiskey, and the other subjects drank water. And then I also had the same subjects who drank whiskey. I also had them spin in a circle, okay? And then the others I had sit still, okay? And then after everything was done, I said, okay, let's see who can walk in a straight line, all right? And it turns out that the subjects who drank whiskey and spun in a circle, they were much worse at walking in a straight line than those who drank water and sat still, okay? So does that mean drinking whiskey causes people to walk erratically, or is it the spinning in a circle that caused them to walk erratically, okay? Well, the way this experiment is set up, looking only at the data, we have no idea, okay? Because all the people who drank whiskey were also all the people who spun in a circle. So maybe people have a hard time walking in a straight line, but we don't know if it's because they spun around or if it's because they drank whiskey or both, okay? We don't know, all right? So, so a experiment that's poorly set up can leave you with, I guess, more questions. You know, is it because of the whiskey? Is it because of the spinning in a circle? Who knows? All right. Does that kind of help what a confounding variable is? Okay.
Can I ask you one?
Yes, sure.
Can you give me an example of more specific for the unstacked and stacked format?
Stacked and unstacked format. Yeah. That's just when we gather data. Okay, we can keep all of one variable in a single column, or sometimes we choose to break them up into multiple columns. Okay, and so I guess in a stacked form, okay. Okay, let's say we went around and we said we asked people how much do you weigh, alright? And then we also ask, you know, are you male or female, okay? So we send out a survey and we say, are you male or female and how much do you weigh, okay? So if it was stacked, we would go like this, okay? A male responds and this person is 190 pounds, and another male responds and this person's 160 pounds, and a female responds and this person is 165 pounds, and another female responds and this person's 130 pounds, and then a male responds and this person is 140, and a female responds and she is 100. Okay? So this is in stacked form. Okay? Everything, all of one variable is in one column, all of another variable is in another column. Okay? In unstacked, okay, we say, okay, let's make a column for males and a column for females, okay? And then we would say, all right, I found a male who's 190, a male who's 160, a male who's 140, and then over here I found a female who's 165, female who's 130, and a female who weighs 100 pounds. Okay, so this would be the unstacked form. In terms of data analysis, computers prefer to have data fed to them in stacked form, generally, okay? But I mean, both of these things present the same information, okay? So that's what we've got going on. So probably this is preferred, okay? But it's not hard to go from one to the other, okay, using a computer. Okay? And it's not that big of a deal. I guess the important thing is, can you look at a table of data and understand what the information being presented, okay? And you should be able to see the difference, see that both of these, like if you saw this table of information versus this table of information, you should understand that they present the same information, okay? Now the form of the information is probably less important than being able to extract that information. Alright, I think we left off last week, we talked about histograms, is that right?
Yeah.
Okay. Alright, so histograms, what kind of variables, what kind of data are we dealing with when we make histograms? Numeric variables, okay? So histograms, we make numeric variables. Or we're dealing with numeric variables. And when we see a histogram, what is it? What does it show us? Okay, so what is what's an important feature in a histogram?
Bars.
Bars, okay. And across the bottom, what do we have? A number line. Okay, we've got a number line across the bottom. And then we have bars, okay? And what do the bars represent?
Frequency?
Yeah, it shows how often that particular numeric value shows up in the data set, right? The height of the bar tells us how often a value shows up in our data set. Alright, then okay, and then when we're describing a numeric variable or a numeric distribution, what are the things we want to talk about when describing the shape? The shape of a numeric variable.
Which way it's skewed?
Okay, so we want to either say, is it skewed or symmetric? Skew left or right? Okay, or symmetric? And then what's the other part?
It's bimodal.
Okay, yeah. How many peaks do we have? Okay, unimodal or bimodal, etc. Great. Okay, and then, all right, so that's for numeric distribution. Okay, on the other hand, if we're dealing with a categorical variable, okay, we can summarize our data with a, what kind of table? Frequency table, right? Alright, so we can, alright, so let's say, okay, we ask, let's say we go around, we ask everybody, who are you going to root for in the baseball playoffs? Okay, so if you aren't aware, Major League Baseball regular season ended, and then now it's playoffs, and there's a playoff game. And so okay, so I don't know. So let's say some people are going to root for the Dodgers, all right? And then was that a yawn or was that a boo? Okay, so we have the Dodgers, and then I don't know. There's other teams. Okay, so you know the Pirates, their first time in the postseason ever, not ever, but in many years. And okay, and then so there's other teams, right? So we go around and we get some numbers here. So let's say these are the only teams people are rooting for. It's not, and let's say so we get 30 and 5 and 12 here. Okay, so I've just made up some numbers here. And, so this is the category or the team. And the frequency. Alright, so this can be presented with a bar chart, okay? Okay, so here's a bar chart. This is not a histogram. Okay. What's the difference between this and a histogram?
They're all closely connected. And there's a number line.
Okay, there's no number line, right? We're dealing with a categorical variable. Okay. And one thing to notice is that the bars here, we can change the order of the bars, and the information in this graph will be exactly the same. Okay, so equally valid would be a bar chart that looks like this. Right? This bar chart presents the exact same information as that bar chart. Okay? And all I did was rearrange the columns. Okay? And I can do that because with categories, the order of the columns don't matter. The order of the categories is completely arbitrary. Okay, so the order here does not matter. Okay. I do not have that option with the histogram, right? Because it's a number line. I can't rearrange the columns because I'm changing the order of the numbers in the number line. Alright. So let's say for a categorical variable, okay, what does it mean to have lots of variation? Okay. So okay, so let's say we were looking at ethnic diversity. Alright, so let's say we made categories for white, black, Latino, Asian, and then other. Okay, and so let's say we have something that looks like this. Other/mixed. Which of these bar charts shows more variation in ethnic diversity? The top one or the bottom one?
Top.
No, bottom.
No, bottom.
What is it?
The bottom, because there's a
The
wider
bottom.
difference between the highest
Okay.
one and the lowest
The
one.
bottom more variation.
More variation. Okay. So, all right. Let's just think about what this might mean. Okay. What city might this be?
Los Angeles.
This could be Los Angeles, right? We're pretty. We got white people, black people, Latino people, Asian people, and then other races, and we've got. Nah, maybe not too many of one or too little of another. Okay, so this could be someplace like Los Angeles. All right. All right, and what might a city like this be? Okay, so this is predominantly white, also a large black minority. Not very many of other
Yeah, Austin.
ethnicities. Okay, so.
Would you have a little list?
Alright, so wherever, right? I'm just making something up. So let's say this is Atlanta, okay? Who knows, alright? Alright, so now if I asked you which city has more ethnic diversity, what would you tell me?
Los Angeles.
Los Angeles does, okay? And so our bar chart would also reflect that same idea, okay? So why would this bar chart have more variation than this one, okay? So this has more variation, alright? So when it comes to variation for categorical variables, the thing to look at for is one category or only a few categories make up almost all of the data, okay? So when looking for variation in categorical data, okay, ask, do only one or two categories account for a large portion of your data? if that's the case, you don't have a lot of variation. If so, not much variation, okay? We're not trying to see if the bars are all the same height or whatever. That's not what we're looking for. What we're asking is, do just one or two categories pretty much make up most of the data here, okay? And so in a place like Los Angeles, we can't really say that just one or two categories accounts for everyone, all right? Whereas, you know, in a place like Atlanta, and no disrespect to Atlanta, it's different. So there is variation, but not as much as a place like Los Angeles. Okay, and so when you finish up chapter 2 in your homework this week, this concept of variation for a categorical variable will also will make an appearance here. Okay, and then it also talks about some dangers with misleading graphs. Is that okay? Let's go back to numeric variables. And we are now going to enter chapter 3. So we're going to deal with numeric variables, and we are looking for summaries of center and spread. Okay? Summaries. So first off, we're going to talk about summaries describing the center. Okay. So let's say we went around and we so let's say we have some test scores, okay? All right, and so let's say a bunch of students took a test, and these were the scores. All right, so let's say 70. Let's throw in a few more. Sorry. There's okay, and then so let's say we got 5. Okay, so here is 15 test scores. All right. Let's make a histogram here, okay? So I can so across the histogram I've got to make some kind of number line, right? So let's say and I'm going to so I'm going to build up a histogram. So I got to figure out how many numbers fit in each bin here. Okay, so let's see. In so at 0 I don't have between 0 and 10 I don't have anything. Okay, so it's actually from 0 to 9, and then from 10 to 19 I don't have any, and from 20 to 29 I don't have any, and in 30 to 39 I have 1. In 40 to 49, I've got 2. 50 to 59, I don't have any.
No, 1.
Oh, I do have 1, okay. And in 60 to 69, I've got 1. 70 to 80, I have 1, 2, 3, 4, 5. 80 to 89, I've got 1, 2, and I have 3? I've got 3. And then from 90 to 100, I have 3, okay? So I should have a total of 15, 6, 11, 12, 13, 15, 16. Did I count wrong?
90 to 100, yes.
Yeah, 90.
Alright, 9 to 100, I only have 2. Okay, so let's build this. I got okay, so my histogram looks something like this. Okay. Is that alright? Are there any questions on how I got this? So what might we say is the middle? Okay, or some idea of center. Okay, so we've got one idea, which is the mean. All right, and that we get the mean by adding up all the numbers and dividing by how many numbers we have. Okay, so this is add up all the numbers and divide by how many you have. Okay. Symbolically, we call this x bar. Sometimes we'll write y bar. It's the same thing. Okay, pretty much between x and y. And to say that we add up all the numbers, we use this thing, which is it looks like a sideways M, but it's the Greek letter sigma, and it means add up. Okay, add up all the numbers x. Okay, x is basically each value that we recorded. Okay, we recorded 15 test scores, so we're going to add up all 15 values. That's what sum of x stands for. Okay, and then to show that we divide by how many we have, we put we make it a fraction and we say divided by n. All right. So x bar is another way of saying the mean, and we say sum of x over n. Okay. Each x, n is the number of items in the sample. Okay. And so that is what I get for the mean. Okay, so what is the mean test score here? Well, I would have to add up 270 plus 55 plus 93, so on and so forth, all the way to the last number, plus 70 plus 40, and then I would divide by
15.
15. Okay. So it's just-
69.5.
Is that right? 69.5?
Yeah.
Someone else also confirm.
Yes.
Alright, great. So my x bar is 69.5. This is the mean. And this could be thought of as the balance point in our data. The balancing point in our data. And so an idea of the balancing point in our data is, let's say this thing were on a seesaw, okay, and we wanted to keep this in balance. Where would I put the fulcrum or the triangle here? Okay, well, if I put the triangle over here, I said the balancing point is over here, what's going to happen? This whole thing's going to fall like this. And if I put the balancing point over here, the whole thing's going to fall like this. So if I put the fulcrum or the balance point at the mean, 69.5, so right around here, okay, that's where it's going to stay in balance. Okay, so the balance point goes at the mean. So this is an idea for a measure of center. Is that okay?
So that's the center of the
It's the mean. The mean.
Okay.
Okay. We'll talk about right now. I'm also going to mention the median, which is another idea for the idea of where is the middle or where is the center. Okay. So the median is also another idea for the center. Okay. This is another measure of center. Okay, and don't worry about this word measure. Okay, it's not that you're like taking things and measuring things. Okay, it's just kind of like it's an indicator of where the center might be. Okay. All right. Okay, so the median here, this is the central point. Okay, this is the spot, a number where half of the data is larger and half is smaller. Okay, so this can be thought of as the middle point. Okay. Half of the data is larger than the median. Half is smaller. guys familiar with percentiles? You've probably heard of that word, okay? The median would be the 50th percentile, okay? Okay, and percentile can also be written percentile, okay? The 50th percentile. And what does that mean? Whenever you hear the word percentile, it means at that number, at the 50th percentile, 50% of your data, or 50% of the population, has scores or numbers lower than the 50th percentile. Alright. So what percentage of people have scores lower than the 80th percentile? 80%. Okay, so at the 80th percentile, 80% are lower than the 80th percentile. At the 10th percentile, only 10% are lower. Okay, so 10th percentile is generally on the lower end, whereas 90th percentile would be something in the high end. Okay, so the median is the 50th percentile. It's smack in the middle. So how do we get the median here? Alright? Well, the first thing we have to do is we have to put all of the numbers in order from smallest to largest, okay? So, it's hard to do this when you're at the board, but I'm going to do my best, okay? So I'm going to do 38,
40,
40,
40.
40, I've got 55, and then 65, and then
70.
70, maybe another 70, right?
Yeah.
And then a 75,
70.
75, 77, an 80, 87.
There's two
No,
80s.
it's two 80s, an 87,
93.
and 93, and 98. Okay, I think that's everyone. There should be 15 numbers there. Okay, great. So they're in order from smallest to largest. So now, the median is the number in the n plus 1 over 2th position. Okay, so the okay, the median is not n plus 1 over 2. It's the number in the n plus 1 over 2th position. So what does that even mean? Alright, what is n? You guys remember what n is?
The number.
The number of numbers, right? So what is my n here? 15. Okay, so here I've got n is equal to 15, the number of numbers. So n plus 1 over 2 is equal to what? 15 plus 1 divided by 2, and that gives me 8. So the median is the 8th place number. It's not, the median is not 8, it's the number in the 8th position.
7.
Alright, so I've put these in order from least to greatest. So this is 1, 2, 3, 4, 5, 6, 7, 8. This is my 8th place number. So my median is 75. Are there any questions on that?
I'm
Yes.
sorry, can you repeat the 15 plus 1 divided over 2, and then you got 8?
Yeah.
I get the 8, but I know that it's the 75, but where did you get it? In the equation. 16 divided by 2, okay.
So yeah, 15 plus 1 is 16, divided by 2 is 8.
Okay, got it.
Okay? So I just took n and I plugged it in and I got 8. So my median is the number in the 8th position, and that is 75. Yes?
Why did you put the 1? Why can't it just be that, like, the middle number?
It is the middle number. N plus 1 over 2 gives you the middle number. Okay? That's just how it goes. Okay, so let's say we had alright, so let's say this is our data set, okay? So let's say somebody else comes along and joins the class and takes a test, okay? And let's say that person scored really poorly, and that person scored 15 on the test, okay? What is the median of my data set here? Okay. Well,
6, 7, yeah.
so what is my n now?
8.5.
So, okay, so my n is
16.
16. Alright, so n plus 1 over 2 is going to be 16 plus 1 over 2, and I get 8.5. So my median is not 8.5, but it's the 8.5th number. It's the number in the 8.5 position. Is the number in the 8.5th position. Alright, so let's think about what that means. Okay, so all of my numbers are still in order from least to greatest, right? So, because that's the number 1 step. So I'm going to number these. This is my first, second, third, fourth, fifth, sixth, seventh, and this is my 8th place number, and this is my 9th place number. Okay, 9th, 10th, so on and so forth. So I don't have a number in the 8.5 position, but I have my 8th place number and my 9th place number. So the number that's in the 8.5 position is the number that's in between my 8th place number and 9th place number. Okay, so 8th place is 70, and what's my 9th place number?
75.
75. Okay, so 8th place and 9th place is 75. So what is in between here?
72.5.
72.5. Now, if you are not so quick, okay, to get the number that's in between here, you can just take the mean of these two numbers. Just take the average of these two numbers. So I would do this plus this divided by 2, and I get 72.5. This is going to be my median if these were my 16 numbers. Okay. Is that all right? Okay. So let's recap. What was my mean when I looked at all 15 of my numbers?
69.5.
My mean was 69.5. And what was the median?
Median was 70.
My median, when I'm just looking at the 15 numbers, my median was 75. So these are both, they give us an idea of where the center is, okay? Or I guess sometimes we have an idea of what center should mean. So maybe you can think of it as, you know, where's the heart of the data, okay? Because heart is kind of this idea of where's the center, but then there's no real, it's not as well defined, right? Where would you say, you'd say, where's the middle of the United States? You'd probably say Kansas, okay? And then you'd say, okay, well, where's the heart of the United States? That's a lot tougher question, okay? Maybe it's still Kansas, okay? But here we've got the mean and the median, and these both give us an idea of where's the heart of our data, or where's the center, or this middle idea of the thing. But we don't have the same number, okay? So what's the deal here? Okay, so these both tell us about the center, but they will not always necessarily be the same thing, okay? But they may not be the same number. Well, what does the median tell us again?
The center. No.
Okay.
Oh.
Well, and so does the mean, okay? The mean and the median both tell us the center.
Middle point.
The middle point, alright? It's the 50th percentile. So we could say, for this test, half of the class, 50% of the class, scored over 75. 50% of the class scored lower than 75. So that gives us an idea of where the center score was. Okay. But the balancing point, the mean, is 69.5. Okay? So if half of the class scored over 75, how much of the class scored over 69.5?
Half of the class.
Well, we don't know exactly how much, but we do know that more than half scored over 69.5, right? Because exactly half scored over 75, and so if I'm going lower than that, more than half scored over 69.5. And we can kind of see that, right? So here we got, if we drew the line in our data, we have 6 people scoring below 69.5. 1, 2, 3, 4, 5. And I've got, I'm sorry, 5 people scoring lower than 69.5. And that means I got 10 people scoring over 69.5. With 75, I've got about 7 or 8 above and 7 below. So the idea, the mean and the median, they both give us the idea of the center, but one takes into account kind of these lower points, and that's the mean. So the mean is affected by outliers. By outliers or other points that are far away from the center. Okay, so what's happening is that these people who scored, a 38 or a 40 on the test, they're bringing the average of the class way down. Okay, so they're bringing it away from 75 down to someplace like 70, 69.5. The median, because it only cares about the point where half are larger or half are smaller, it doesn't care what these extreme points are. This lowest test score could have been a 0, okay? And the median would still be the same at 75. If I change this lowest test score to a 0, what would happen to the mean? Yeah, it'll get even smaller, right? Because the mean is found by adding up all the numbers and dividing by 15. So if I added up all these numbers and this one was a 0, that total number would be smaller. And then dividing by 15, that number will be less than 69.5. It'll be something around 67. Okay, so the mean is affected by outliers. So because of this, some people say the mean is more useful for symmetric distributions, and the median is more useful for skewed distributions. I don't necessarily agree with that, but there is some validity to that point. Okay, so the mean and the median, they both give you an idea of center, but they also have, I guess, different purposes. Okay, so. So some say symmetric and use median for skewed situations. But the truth is whether it's symmetric or skewed, you can find the mean or the median. Okay, so both, you can find the mean or the median for both symmetric or skewed situations, and they will both give you an idea of center. Alright, and I guess if you can write somewhere that the median is not affected by outliers, okay? So those are our measures of center. Alright, so now measures of spread or dispersion or variation. These are all kind of similar ideas. And the idea here is, are the numbers in our data set, are they close together or are they far apart? So what is variation? Are the numbers similar to each other? Are the numbers in our data set So if the numbers are similar to each other, we say there is little spread or little variation. And if they're very different, we say there's lots of spread or high variation. Alright, so let's just let's test if we can understand this concept. Okay, so let's say these are all test scores here, okay? These are different tests given. Okay. So which one has the least variation? So which one has the least variation? Yeah, okay, so this one has the lowest variation. Alright. And in this test, most of the students scored 80 to 90, or kind of in the 70 to 100 range. Alright. And so in other words, the scores are pretty similar to each other. Sure, we have a couple students scoring between a 60 and 70, but nearly all of them got between a 70 and 100, so pretty similar here, okay? So nearly all students scored between 70 to 100, okay? We could even refine this and get more detail. Okay, which one has the most variation?
That one.
The bottom one.
This one? Or that one?
That one because it's all.
Yeah, this one has the most variation. Okay. Here the scores are wildly different from one another. Okay. This could be like I don't know, a foreign language test or something. Okay, where and you're giving it to a group where some of the students understand this foreign language and others have no idea. So you have some students doing very, very well, and other students doing absolutely terrible. Okay, because these people are just guessing or leaving the whole thing blank. All right. So this has the most variation. The scores are very different from one another. Okay. Are very, very different. Some are very high. Some are very low. Okay, and this one somewhere in between. Okay, we've got a much larger range of scores. Okay, than this one, but the scores aren't as wildly different as they are over there. Okay, so this is somewhere in between. Okay, so we have, most are in this middle range. Okay. Some are high. Some are low. But not that many, okay? Over there you've got some that are, over here we've got a lot that are extremely high and a lot that are extremely low. Alright. Now, here these are kind of extreme examples, so it's easy to eyeball and get an idea of what has high variation or low variation, okay? But maybe we want a more specific way, rather than saying, if I show you two histograms, and rather than just saying, that one looks like it's got more and that one looks like it has less, maybe we have more concrete ways to figure out spread and variation. So So one of these ways is called the standard deviation. This is a way for us to measure the variation or the spread in a data set. What kind of variables do we use the standard deviation for?
Numeric?
Numeric, okay? We use the standard deviation for numeric variables, okay? What about the mean and the median?
Numeric.
Numeric, okay? So we do not have mean or median for categorical variables. We do not have standard deviation or any of the other numbers we're talking about today for categorical variables. So everything, all of these summaries that we're having here, all of these numeric summaries apply to numeric distributions. What's a summary that we can use for a categorical variable? Okay, so well, how can we summarize categorical variables? Okay, bar charts and frequency table, right? So what do we put in a frequency table?
Frequency?
The frequency, okay? So that's one way to summarize a categorical variable. The frequency or the count, okay? And if we turn this into a relative frequency table, what do we use instead?
Use percentages?
A percentage, okay? So percentage is also another way to summarize a categorical variable. So percentages and counts are percentages and frequencies, or percentage is the same thing as a proportion. So those are all ways to summarize categorical variables. All of these other things we're learning, mean, median, standard deviation, later on we're going to learn range and IQR. Those are for numeric variables. Okay, so the standard deviation is a way for us to measure the variation or spread in a data set, okay? One way to think of the standard deviation is to think of it as the average, quote, distance or typical distance our points are from the mean, okay? This is a very loose definition, okay? So the idea is the, quote, typical distance a point is from the mean. So let's okay, so let's talk about two families. Two families, they both had, let's say they both had 5 children, okay? So we have, I don't know, one family, okay? So family 1, do we have a name for this family? The Johnsons? Okay, sure, the Johnsons. And let's say their kids go, the oldest is age 18, and then they have a 14-year-old and a 10-year-old and a 5-year-old and a 2-year-old, okay? So that is the Johnson family, all right? And family 2, the Millers, okay, great. And let's say their oldest is 9, and they have an 8-year-old and a 7-year-old, and a 6-year-old, and a 4-year-old. So they both have 5 kids. All right. Now, it's very obvious here, okay? But if I said, okay, which family has more variation in the ages of their children, you would say the Johnsons, okay? And I'm sorry? So the Johnsons, they, well, they're still dealing with a kid who is in diapers at the same time as, the oldest might be going off to college or something like that. Whereas with the Millers, okay, they're all kind of in this, all 5 kids are kind of in the same age range, right? They're all probably going to be going through similar, of course, different issues at the same time, but things are, so the ages here are a lot more similar, okay? Let's talk about the standard deviation and with regard to the ages of the children of the Johnson and Miller families. Okay. There's that. Okay. So let me draw a number line here. And we'll start at 0. Okay, so I'm going to draw dots at each of these children's ages. So I'm going to put the Johnsons above the line. And then I'm going to put the Millers below the line. Great. Okay, and we can even see from the dot plot that there's more spread above than below, right? Okay, so what is the mean age of the Johnson family?
2 plus
Mean age of the kids in the Johnson family. Well, we do 2 plus 5 plus 10 plus 14 plus 18 divided by 5. I get 9.8. So this is X bar for the Johnsons. Okay, and X bar for the Millers. So far, so good?
Mm-hmm.
Alright, so I'm going to draw a dotted line at the mean age for the Johnsons. I'm going to draw a dotted line for the mean age for the Millers. Okay. Alright, so let's just look at the Johnson family. Alright, and we're going to get the standard deviation, what we're looking for is kind of the average distance, or the typical distance that a point is from the mean. And it's not exactly the average, but we'll get there, okay? So how far is the middle child from the average age? What's my average? My average is 9.8, right?
0.2.
So the middle child is 10 years old. This middle child is 0.2 years away from average, okay? So this one is 0.2 away, alright? How far away is this child from average? 4.2, right? How did I get 4.2? I did 14 minus 9.8, right? Okay, and how far is this child from average? 8.2, right? I do 18 minus 9.8, and I get this person is 8.2 away. Is that okay with everyone? All right, and how far is this child away from average? Yes, I do 5 minus 9.8, and this one is 4.8 years lower than average. Okay, and this one 7.8 lower, right? 2 minus 9.8, 7.8 years away from average. So we've got the average age at 9.8, and we're figuring out how far away is each child from this average. Okay, and so we said this one, you know, is 7.8 years younger than average. This one's 4.8 years younger than average. This one's 0.2 years older, and I go on and so forth and so forth. Okay. All right. So this is where it just gets a little bit weird. But for the standard deviation, rather than adding these up and dividing by 5. Okay, taking these distances, adding them up and dividing by 5, I'm going to square everything first, okay? All right, so that's just something we do as statisticians. We like to square a lot of things, okay? So what does it mean to square something?
On the root?
Times it by itself.
Yeah, multiply it by itself, right? So we're going to square each number. So we're going to multiply it by itself, okay? So I'm going to do 7.8 squared. And then, and I do 4.8 squared, and then 0.2 squared, and 4.2 squared, and 8.2 squared. Okay, and then I'm going to find the average of those squares. Well, almost. Okay, so I'm going to add all of these up. How many numbers do I have?
5.
I have 5. So you'd think I'd divide by 5. But just go with me. We're doing this weird thing. Instead of dividing by 5, I'm going to divide by 4. I'm going to take 1 away from 5, and I'm going to add all of these up and divide by 4. Okay. And when I get that number is known as the variation. Okay, so the resulting number here, this is the variation. So I do 7.8 squared. And I get 60.84. Point 2 squared is 0.04. So I have all these numbers to add up. And then now I divide by